Okay, for the next section, we will cover about Newton-Raphson Method. Okay. Newton-Raphson Method. Okay, so this method will give us the exact value for the roots of the equation. Okay, not the exact, that almost exact and better than the previous one that we already learned. Okay, so Newton-Raphson method is actually based on the tangent of the curve. So based on the tangent of the curve. Okay, and the second thing is to let x equal to x naught be the first approximation. Okay, about this we will be look at this explanation lah. Okay. Okay, let's say we have a graph of y and x axis. Okay, so the graph cuts the x axis where the intersection between the graph and the x axis is labeled as the alpha. So the alpha is the root, then the root lies in between the interval of a and b. Okay, let's say it's a and b. So on what we have learned before, we only mentioned the interval, so that means the roots of the function or the equation can be any number between the interval. Okay, so now Newton-Raphson method wants us to narrow down our interval to find the almost exact value of the root. Okay, what we want to do is we assign x naught. So x naught will also be in between the interval of a and b. So x naught will have a point on the graph that is labeled as S. So then from the point S, we draw a tangent to this line. So this is the tangent to point S. So that will intersect to a point on x-axis, and then that will be labeled as x1. So what we want to say here, that x1 is a better approximation to the value of alpha than x0. Okay, because x1 is more closer to the alpha, so x1 is more accurate than the x0. Okay, so what we want to do next is we focus on the tangent of the point S. So the tangent of the point S is actually the derivative of the function, because it is in the form of dy over dx. So then it is a gradient. So f prime is equal to f x naught. Okay, it will be the f x naught minus 0 over x naught minus x1. So this is just the formula of a gradient, where m equal to y1 minus y2 over x1 minus x2. Then what we have here is f prime x equal to f x naught over x naught minus x1. So we rearrange this equation so that we have the x1 as the subject of the equation. So that will be x1 equal to x naught minus f x naught over f prime x naught. Okay. Oh sorry, I forgot to write down here. This is f prime x naught. Okay, f prime x naught minus f x naught minus 0. Okay, so in order for us to find the value of x1, we can use this equation. So x1 equal to x naught minus x naught over f prime x naught. Okay, so now let's move deeper about the explanation of Newton-Raphson method. Okay, just now we already know that above the point of x naught, we have a point that is called as S. So S lies on the graph. So this is a line. So from point S, we form a tangent to point S and intersect on a point that create x1. This is x1 and this is x0. So x1 is based on the tangent that touch the S point on the graph. So from x0, so as mentioned before, x0 is a better approximation of the value of alpha because it is closer towards alpha. So in order to get more closer value towards alpha is that we just need to repeat the same process. So x0 then creates another point on the graph. So this is called as t. Okay, so then this t will have a tangent of point t that will intersect on x2. So that let's just name the point above x2 as the R that touches the graph. Okay, so from here we can know that x2 is a better and closer approximation to the value of alpha because x2 is much more closer towards alpha than x1. So to find the value of x2, we can use f prime x1 equal to f x1 minus 0 over x1 minus x2, just the same equation of the gradient, but now it based on the point of t. So then we rearrange the equation. We will have x1 minus x2 equal to f x1 over f prime x1. So the value of x2 will be equal to x1 minus f x1 over f prime x1. Okay, so this is the value of x2. We can find the value of x2 by using this formula, just the same formula as we already learned just now. Okay, so in order to get much more better approximation of value of alpha, so we can create x3. So x3, the equation of x3 will become x3 equal to x2 minus f x2 over f prime x2. So x3 will give us a much more better approximation of value of alpha. So it can be generalized here that the value to find the approximation, the formula to find the approximation of alpha can be written as x n plus 1 equal to x n minus f x n over function prime x n. So this is what we call as Newton-Raphson formula. Okay, before we proceed to example of question for Newton-Raphson formula, we need to take note that Newton-Raphson model does not always work. Okay, kenapa sometimes it does not always work? It based on the graph that we want to find its root. Okay, for example, we have this kind of graph. So this will be the roots of alpha, and let's say our x naught is right over here. We start with x naught right over here. So when we have x naught, we try to find the point above x naught that we call before as point S. So from point S, we form a tangent line. So that tangent line, we create x1. So x1 is actually moving further away from alpha. So this means x1 is not giving better approximation of alpha than x0. And then from alpha, it creates a point of t. So then the tangent of t is moving towards x2. So x2 is moving towards alpha. So this is not consistent, as x0 firstly moving further and then it moving forward, moving closer to alpha. So this is why Newton-Raphson model does not always work. Okay, one more example is when we have a graph of this shape. Okay, let's say we want to find the alpha value right over here, and we have a point of x0 over here. So the x0 create a point that we call as S. Then the tangent of S creates create x2. So x2 will be over here. So then x2 create point T. So then point T, tangent of point T right over here, it creates, oh sorry, this at first it create x1, then it create x2. So this is not consistent, as the x1 firstly moving further away, then moving closer. So this is the situations where Newton-Raphson model is not working. Okay, now let's look at an example of solving questions using Newton-Raphson model to find the approximation value of alpha. Okay, so this is the question. Show that there is a solution of x cubed plus x minus 3 equal to 0 between x equal to 1 and x equal to 2. Use Newton-Raphson model to find root correct to 3 decimal place. Okay, so it is mentioned here that there's a solution that lies between x1 and x2 for the equation of x cubed plus 3 minus plus x minus 3. So we know that the function is equal to x cubed plus x minus 3 equal to 0. Then let's first try substitute the value of x equal to 1 and x equal to 2 into the function. So then we have x1 equal to 1 power of 3 plus 1 minus 3. So this gives us negative 1. And f2 is equal to 2 cubed plus 2 minus 3. And this is equal to 7. Okay. So from here, we can see that function 1, f1, give us negative 1. So this is less than 0, and f2 give us 7. So this is bigger than 0. So there are two different signs. One is a negative and another one is a positive. So from here we can make a conclusion. We can justify that there is a root between one and 2. Okay, so now let's move to the Newton-Raphson method, or it's not model, it's method, sorry. Okay, now let's move to the Newton-Raphson method to find the approximation value of the root. Okay, to find that, first we differentiate the function, and that gives us 3x squared plus 1. Okay, so 3x squared plus 1. Okay, so the interval mentioned here, there is a root between 1 and 2. So in between 1 and 2. So now let us start our x naught with a value that is in between 1 and 2. So just take the middle one lah, for example, and make it easier. Just take x naught as 1.5. So that is in between 1 and 2. So 1.5 as initial approximation. Okay, so now let's refer to the equation of Newton-Raphson method. So the equation is xn plus 1 equal to xn minus f xn over f prime xn. Okay, so now let's first find the x1 because we already have x0. So then we have x1 is equal to x0 minus f x0 over f prime x0. So we substitute the value of x0, that is 1.5 minus f x0. So that is 1.5 power of 3 plus 1.5 minus 3 over 3 1.5 square plus 1. So this is the formula. So you can press your calculator and find out that the value for x1 is equal to 1.258064516. Okay, just take all the value written on your calculator, because usually for Newton-Raphson method they sometimes ask for a high number of decimal place because that is an approximation. Okay, so to get x1 is not the final answer. What we need to do next is to find the x2. So x2 will be x1 minus f x1 over f prime x1. So you substitute the value of x1, this value, into the formula. So that will be, so you can use calculator, pause the video, calculate by yourself, and you will get that x2 is equal to 1.214705333. Okay, so now let's compare the value of x1 and x2. So x1 is 1.25806, meanwhile x2 is 1.2147, and the question asks an answer up to 3 decimal place. So we get at first decimal place of x1 and x2, they are not the same number. So this means we need to find a more closer approximation. So we need to proceed to x3. So x3 is equal to x2 minus f x2 over f prime x2. So x3 will give us the value of 1.21341276. So compare x2 and x3. The first 3 decimal place is still not the same number. So then we proceed to x4. Okay, to x4 is equal to x3 minus f x3 over f prime x3. So this is equal to, you can use your calculator to find the value. So x4 is actually 1.213411663, and we compare x3 and x4 has the same number for the first 3 decimal place, and the question wants up to 3 decimal place. So the same number 1.213 and 1.213. So if the first 3 decimal place is the same number, so we can stop our calculation over here, and we can mention that the root is 1.213. Okay, if you go further closer to alpha, let's say you want to find x5. Okay, I already calculated x5. So x5 is equal to 1.213411663. So the first 3 equation, so the first 3 numbers also give the first 3 numbers for x4. So the yang belakang tu is not important anymore, because the question only want up to 3 decimal place. So the other decimal place up to 3, you can neglect that number. So that's why you can stop your calculation when you get to x4, where the decimal place, the first 3 decimal place is equal to x3 of the x3 first 3 decimal place. So that is 1.213. So our final answer is 1.213. Okay, now let's look at our next example is to determine unit interval which contain positive root. Of equation 2x square minus 3 equal to 1 over x. Okay, then use Newton-Raphson method to find its roots, to find this root to 2 decimal place. Okay. Okay, so take middle value of interval as initial approximation. Okay, so first we need to find the root of the equation, the interval for root of equation 2x square minus 3 equal to 1 over x. So this related to our previous section that we have learned. So by using trial and error, so we have fx that is equal to 2x square minus 3 minus 1 over x equal to 0. Okay, forgot to mention that you can pause this video and try it by yourself, and then you can continue to check your answer whether it's true or not. Okay, so let's try with x equal to 1. So then we have 2, 1 square minus 3 minus 1, then we get here is negative 2, that is less than 0. And for f2 equal to 2, 2 square minus 3 minus 1 over 2, and this is equal to 9 over 2. So this is bigger than 0. So from here we can justify that we have a root within the interval of 1 and 2. Okay, so we have already identify the interval for the root, and then we continue for the next question is to use Newton-Raphson to find this root to 2 decimal place and take middle value of interval as initial approximation. So the question wants us to let x naught equal to the middle of the interval, so that is 1.5. So then we proceed to x1. So x1 is equal to 1.5 minus 2 1.5 square minus 3 minus 1 over 1.5 over 4 1.5 plus 1 over 1.5 square. Okay, so the denominator of this fraction comes from the f prime x. Okay, you can find the f prime x. You differentiate the equation, then you substitute the value of 1.5 into the equation. So then you will have the value of x1 as 1.37068965, and the question 1, the answer up to 2 decimal place. But first we proceed to x2. So you substitute value of x2 into the formula, and you will have 1x2 equal to 1.3660312228. So the first 2 decimal place is not the same as x1. Then we proceed to x3. So x3 is 1.3660254404. Okay, so now we compare x2 and x3. We can see that the first 2 decimal place is the same. Then we can conclude here that the root of the function is equal to 1.37. We round up it to 2 decimal place. So that is our answer. Our next example is to sketch graph. Sketch graph of y equal to exponent power of x and y equal to x plus 0.5. Then find interval for the roots. There is a in between a and b. Then solve the equation of x exponent negative x equal to x plus 0.5 by using Newton-Raphson, okay, and R is Newton-Raphson method, to 4 decimal place. Okay, so what we need to do first is to sketch the graph. Okay, so the graph of exponent to the power of negative x, so y is equal to exponent power of negative x. Okay, right here is negative x. So the graph will intersect at y equal to 1. Okay, so this is the graph of y equal to exponent to the power of negative x, and the graph of y equal to x plus 0.5. So it will be have y-intercept at 0.5 right over here. So it set lah kat situ. Okay, so this is the graph. Okay, so from these two graphs, we look at the intersection. So this is the point of intersection. So the point of intersection indicates the value of the roots of the equation of the function. Okay, from the graph we already know this is the point of origin, so this is 0. So then we didn't know the right side of the interval. So how do we find the right side of the interval? Is to determine the next integer. So the next integer will be equal to 1. So y will be equal to exponent to power of negative 1. So y equal to exponent to power of negative 1, and that will be, use your calculator, then you will have y equal to 0.3679, and for here we try to substitute y equal to 1. So y equal to x equal to 1 plus 0.5, so then we have y equal to 1.5. So these two value is not the same, where we have y of this graph is 1.5, and y for this graph is 0.3679, which means the red one graph will be above, higher than the exponential graph. So this will be the value of 1, because 1.5 is bigger than 0.3679. So this will be the point of 1.5, and this will be the point of 0.3679. So the interval will be in between of 0 and 1. Okay. Next is to solve for the function to find the exact approximation of the roots. Okay, so to find the approximation, we take x 0 equal to 0.5, the middle one between 0 and 1. So then we proceed to x1, mean 0.5 minus exponent to the power negative 0.5 minus 0.5 minus 0.5 over negative exponent negative 0.5 minus 1. So the denominator is the derivative of the function. I forgot to mention the function. The function is fx equal to exponent negative x minus 0.5. Okay, so by calculation, use calculator, then you get your value of x1 equal to 0.255081337. So we need to proceed to x2. So substitute the value of x1 into the equation. So then you will have x2 equal to 0.266221487. So compare the first 4 decimal place. The first 4 decimal place is not the same. Then we proceed for x3 equal to 0.266248608. Okay, so from here we can know that our first 4 decimal place is the same as x2. So we can mention that the root is x equal to 0.2662. Alright, so that is our final answer.